Our next speaker is Dr. John Daugman. This is, I referred in introducing the last speaker to the attraction of Cambridge of somebody who'd been here and gone away, returning from across the Atlantic. We have another speaker who illustrates this theme, but in a more advanced form, namely not returning, but coming new from across the Atlantic. We imported John Daugman, who began his career at Harvard, where he became a faculty researcher. He then, after a spell in Tokyo, came to Cambridge, in fact, to the zoology department, and we succeeded in poaching him from zoology. John Daugman.
Good morning. I'd like to talk to you a bit about an application of work in computer vision and statistical pattern recognition, and particularly wavelet theory in signal processing. This is the study of iris patterns for purposes of identification and use in applications in which one either needs to establish or confirm or determine the identity of a person based on the premise that the structure you see here in the iris of the eye is a random pattern of sufficiently high dimensionality, sufficient stochasticity, sufficient complexity that it will be unique to each eye and therefore can serve as a kind of fingerprint that is externally visible, that can be acquired from some distance. Let me just remind you that the iris is an internal organ of the eye behind the cornea and the aqueous humor. It's the colored part here, and of course lying in front of the lens, and the hole in the iris forms the pupil. That's the purpose of the iris, of course, is just to control the amount of light that enters the eye. And so you have, I guess it's the only internal organ of your body that's externally visible, and externally visible from some distance. We have a long tradition of sort of looking at the eye as a kind of, if you will, the window to the soul. There's this tradition in literature of thinking of the eyes as somehow speaking, as I think Portia in The Merchant of Venice is described as emitting speechless messages from her eyes and so forth. So I want to take that a bit seriously and ask whether we can actually extract information that's useful from iris patterns. Let me show you some color images of irises just to give you a flavor for the kinds of patterns that exist in the iris. There's clearly a lot of random variation there. You can measure mathematically the, can I make that right? No, I guess not. One can quantify the degree, the sort of dimensionality of these patterns, how many bits can be extracted from them of representing the variability among different irises. And it's really quite an interesting and challenging problem. Now, I should say that the analysis of iris patterns is not new. It goes back about 3 millennia to the time of Entope in the Old Empire in Egypt. And over the years, the science of iridology developed, which could interpret your future, your personality, and indeed the state of health of each of your internal organs. It's a bit like palm reading, I suppose. And here's a chart made rather recently by Dr. Bernard Jensen showing how every one of your internal organs gets sort of mapped into the iris, and other branches of this school of science will interpret your future and your personality as well. Iridology is particularly popular today in Romania and in California, especially particularly in the Bay Area for some reason. In fact, I have a directory of iridologists in the Bay Area who have produced, among other things, this chart showing how your personality is revealed by your iris pattern. You see there's mental type, emotional type. This is me over here, extremist type. And this is clearly a subject with a future. In fact, it's occurred to me that if uses of iris analysis for security don't pan out, there's still a future, at least in the Bay Area, in this sort of work. Well, this is not actually the application of iris analysis that I'm going to talk to you about today, although one might imagine that future work in HCI, in the human-computer interface, may well find this use valuable and indeed therapeutic. What are some of the properties of the iris which are both advantages and disadvantages in terms of its use for identification. Well, I've mentioned already the fact that you have a highly protected internal organ, which is externally visible. You can acquire the image from a distance up to a meter or so. These patterns contain a high degree of randomness. One can quantify this by standard techniques in information theory, which allow you to sort of calibrate the informativeness of different dimensions of variability in patterns. How much information do you gain in terms of discrimination, being able to discriminate different classes by extracting those forms of variation. This is the idea of degrees of freedom. You know, a door on a hinge has 1 degree of freedom, a universal joint like your wrist has 2 degrees of freedom, and so forth. Iris patterns, as random patterns, have statistically 266 degrees of freedom, which is quite a bit more than fingerprints, by the way, certainly more than facial geometry generally. If faces were as random as irises, then some people would have 17 noses behind their 4th ear, and somebody else would have 3 mouths, rather like that scene in I think Star Wars, where Luke Skywalker goes into the galactic bar and finds creatures like that. So we have a lot of variation and randomness here that you don't have, for example, in faces or other less variable parts of bodies. The actual information density, statistically speaking, of iris patterns is measured by the entropy, which you get from the distribution of comparing different irises. The entropy works out to 3.4 bits per square millimeter, a number to remember. And of course, the uniqueness of iris patterns is a consequence of the combinatorial complexity of how many different kinds of combinations of patterns or features you might find in a given iris. And that generates factorial and binomial sized spaces of possible patterns, and that is the real origin of the uniqueness of why you can encode irises in such a reliable way as a unique pattern. The encoding and decision making is tractable. It's fast. It takes about 1/10 of a second to generate an iris code from an iris pattern. Some of you may have seen the demonstration upstairs. It has some other properties, like the fact that there's a pupil which is constantly oscillating in size. So the oscillation is called hippus at about half a hertz. In addition to the fact you can, of course, drive the pupil size if you wish with light. So this is a way of confirming you're looking at a living iris, not a photograph, for example. It has a prenatal morphogenesis. It begins to form around the 3rd month of gestation and is complete around the 7th or 8th month of gestation, although after birth there is often a change in color because a blanket of chromatophore cells covers the iris in the first 3 months. So that's why most babies are born with blue eyes. That's the absence of pigmentation, and then they go on to develop their genetically determined pigmentation. Speaking of genetics, an important property is the lack of genetic penetrance of iris patterns, which means that identical twins have completely uncorrelated iris patterns. And this is an advantage over, for example, DNA testing. Something like 1 person in 120 in the population at large has an identical twin, which means that over the population, DNA testing must have a false accept rate or false match rate no less than 1 in 121, which is not very good. I'll show you some data on the lack of genetic penetrance in these patterns in a moment. And the pattern is apparently stable throughout life, despite Imtope and the iridologists in San Francisco. Of course, the iris has disadvantages as well. First of all, it's a small target, about 1 centimeter in diameter. You want to acquire from a distance of 1 meter. That's challenging. Besides being a small target, it's a moving target. The eye moves in the head, which moves in the body. So, moving objects also makes it difficult. The pattern is located behind a curved, wet, reflecting surface, the cornea, which means you always get a wide-angle mirror reflecting the world in front of the person back into the camera. So you have the superposition of structure on the iris, and you have to play games with wavelengths to remove that. The iris is often obscured by eyelashes, lenses, reflections, and other forms of corruption. We have to be able to tolerate quite a lot of corruption in the iris image. It's occluded by eyelids, often drooping eyelids. It deforms non-elastically as the pupil changes size, so you need a fairly sophisticated mathematical model of the deformation in order to invert it to get the same iris pattern regardless of the diameter, the size of the pupil. And of course, the illumination should not be visible or bright. This is, after all, somebody's eye. You don't want to be shining a bright light up into it to get the image. You have to use infrared light. And finally, socially, I think there's a potential problem in the acceptance or uptake of the technology related to the fact that it has some Orwellian connotations, perhaps. This is, after all, the country that gave us George Orwell. Well, weighing these pluses and minuses in the balance is, I suppose, what some of the current is the purpose of some of the current trials that are going on around the world. There are tests in Japan, Korea, the US, and in Britain. You've probably heard of the Nationwide Building Society's trials, which went on for 6 months and terminated recently very successfully. And it remains to be decided whether it will actually come into use. Let me now tell you a bit about some of the technical aspects of how it all works. I'd like to describe how the pattern is isolated and encoded and what its statistics are. And what kind of reliability and performance one gets using this method of identification. Of course, you have to first find the eye in the field of view, and that's something that's rather conveniently achieved by the use of wavelets. I'll tell you more about wavelets later. It's a rather important new field of work in signal processing, image processing, and it's sort of taken over computer vision in the last few years. Facial features are what we want to find so we can understand what a face is, understand what the different features are in a face. And I think the appropriate point of view here is that facial features are localized undulations, having a size, a position, a phase, a symmetry. In other words, they have the same parameterization as wavelets have. Wavelets are localized undulations, parameterized for size, position, and phase, and orientation. This is a rather different point of view than I think traditional classical work in machine vision, which saw the world as made up of manufactured objects with smooth planes, straight lines, and right angles. And faces, on the whole, just aren't like that. They're sort of floppy and wavy, and they have continuous variation, continuous structure, continuous differentiable, if you will, structure. So by convolving an image with these complex valued Gabor wavelets that I'll tell you about shortly, we get real and imaginary outputs whose modulus is a distribution of energy that peaks where there are facial features. So this is a way of mathematically taking seriously the view that facial features are localized undulations and we want to find where they are. Here you see the energy, the modulus of the real and imaginary parts superimposed on the original face here, and it does a fairly good job of finding the main features of the face. We then have to be more precise and localize the individual boundaries of the iris, which includes the pupillary boundary, the outer boundary, the limbus, where the iris meets the sclera, the white part of the eye, and of course the eyelid boundaries itself, because we don't want to encode eyelids or eyelashes, we want to extract this part. And this is a nice opportunity for some efficient numerical computing, numerical representations of mathematical operations like this integral differential operator here is a very good way to find all of these contours. What you see here is a contour integral being computed, the integral of luminance, the image around some contour, which is parameterized by the 3 parameters of a circle, center coordinates and radius. And we wish to take the derivative of that integral as a function of radius, smoothing it with some smoothing function g, and look for the maximum of that operation. And that's an excellent, it's really a circular edge detector in English. It's a circular edge detector. The derivative is large where there's a transition, a large change in the image. The integral makes it a statement about some whole region or area in the image. And looking for the maximum of that tells us where the most energetic edges are, which form arcs that can be fit by splines. Here you have a third-order spline to describe the eyelids and simpler curves to describe the iris boundaries. It's not that hard to find irises, after all. It has a rather distinctive circular geometry. And that whole process is very fast. Now, there is a lot of corruption in these images in general. You have, of course, eyelashes, and often people wear hard contact lenses, which leave these pronounced artifacts. You wouldn't want your recognition algorithm to, basically be detecting contact lenses and classifying on the basis of contact lenses or eyelashes and so forth. And so there's a certain amount of AI that goes into the problem of knowing what is tissue and what is other kinds of structure. Here you see an algorithm output that it highlights in white where it finds structure that it knows is not iris pattern, but rather eyelashes and other artifacts. And as I've sometimes said, we have to tolerate so much corruption in these images in the general population that one feels a bit like an Italian politician. Now, how do we actually set the bits in an iris code? This is, I guess, the most mathematical part of the process. It's this principle of demodulation. This is what Gabor wavelets look like. They are complex valued functions, having a real part and an imaginary part, a bit reminiscent of the Bessel functions, which Morris Wilks mentioned yesterday in some of the early computational tables that were generated by EDSAC. I guess using that wonderful phrase of Douglas Adams, these are almost exactly, but not quite unlike Bessel functions. They have, this is, in a certain sense, all of Fourier analysis is a special case of wavelet analysis. If you simplify the parameterization of the wavelets, you get Fourier components and the Fourier transform. So this is a way of, in a sense, building a continuous deformation between the space domain and the frequency domain, rather than having to choose to do all of your analysis in one domain or the other, which is the kind of classical problem in the Fourier domain is a very different point of view from the space domain or the time domain. But with wavelets, you can sort of build a continuous bridge and decide, how close to be in this continuous deformation between those two extremes. Let me just take you through the integral operations. Bits are set based on whether the real or the imaginary parts of this expression, this operator, are positive or negative. So ultimately, we're looking for a simple sign value, SIGN. We take a projection of the image onto a Gabor wavelet, which, as you can see, is a complex exponential representing a Fourier component localized with a bivariate Gaussian in polar coordinates, r theta, corresponding to position in polar coordinates on the iris. So it's just an inner product projection of the image structure onto this operator, and we ask about the sign of the real and the imaginary part. Now, I have to tell you, I went to school in North Carolina, and they taught us this. This is the main mathematical truth that I carried away from North Carolina. You can't take the square root in a negative number. Now, of course, on the other hand, there's this remarkable Euler relationship, e to the I pi plus 1 equals 0. One of the most extraordinary simple expressions. It sort of unifies many branches of mathematics. We have E, which of course represents analysis. It's the, as a base of exponentiation, it generates the function which is equal to all of its own derivatives. We have pi representing geometry, I suppose. 1 and 0 representing arithmetic. And then we have this creature I, square root of negative 1, that you can't take in North Carolina. And it's a kind of an unusual, it's a special relationship. I mean, how often does it happen in your life that you take a positive number, a good solid Church of England positive number like E, and you raise it to some power and you end up with negative 1. It's kind of remarkable. Of course, this is the familiar foundation of harmonic Fourier analysis is all built upon the use of complex exponentials for analyzing signals, and if you make this a complex exponential function of time or space, you end up with wave patterns. And if you localize them to particular epochs of time or space, then you get wavelets. That's the simple idea. And wavelets are a wonderful way to extract structure. They represent structure that is parameterized, as I said earlier, for size and position and phase and so forth, and they generate codes which lend themselves to pattern recognition. I was struck yesterday in watching the EDSAC film, the 1951 film, to see that most of these operators, I should say there's a quadrature relationship because you have real and imaginary wavelets, and their phase, in a sense, is 90 degrees. And I noticed in the EDSAC film that there were math library calls for quadrature, exponentiation, and so forth. And it occurred to me, gee, I could have done all this in 1951 with EDSAC library calls, math library calls. What took us so long? But I subsequently learned from David Wheeler last night that quadrature did not refer to the phasor diagram in the complex plane, but is a sort of anglicism for numerical integration. But anyway, that certainly would play a role here as well. There's nothing new under the sun. Okay, finally, what do we get when we set? So the idea is to set the bits in an iris code by asking in which quadrant of the complex plane does the projection of iris tissue onto wavelets lie. So setting the bits on the basis of the sign, whether it's positive or negative, the real part of the imaginary is positive or negative, is of course equivalent to asking in which quadrant of the complex plane does the phasor lie when you project the iris onto such a complex wavelet. And that is the entire basis for how the bits are set in an iris code. What are the statistical properties of iris codes? Well, first we have to establish that there is independent variation. This would be useless if everybody's iris had, say, a notch in the 12 o'clock position, then you couldn't recognize people on the basis. Well, then the probability of bits being set would be non-uniform as a function of position in the iris code. The fact that this distribution is uniform makes it a maximum entropy code, and it shows there's independent variation everywhere across the iris code. Their independent bits are being set, and the fact they're set with a probability of 0.5 in each position makes it a maximum entropy code, which is what we'd like to have. So this means that we can perform iris recognition really just by a simple test of statistical independence. In a word, you are recognized when you fail a test of independence against a particular iris code, and you are guaranteed, statistically guaranteed, to pass that test of independence against every other iris. So it's the failure of a test of independence that implements this particular pattern recognition algorithm. I think one often finds in computer science that the key is found by converting a problem that's hard to solve, like recognizing these random patterns of high dimensionality, into a problem that you know how to solve. And in this case, again, there's, going back historically, this is a problem that's been understood for a few hundred years. This is Jakob Bernoulli, who is famous for his work on the binomial distribution, not to be confused with his older brother Johann, who co-invented the calculus, or his younger brother Daniel, who didn't do much of anything. But they lived in Groningen, the Swiss originally. And Bernoulli developed this famous discrete probability distribution for coin tossing, Bernoulli trials they're called. The distribution of, if you toss a coin n times, the probability of getting some fraction m, the distribution for the likelihood of different outcomes, different fractions of outcomes being heads, given that you've done n tosses in a run, and you repeat that run many times, is described by the binomial distribution. And one can implement a test of independence simply by asking how likely it is that two different runs of coin tosses would produce a certain fraction of bits of outcomes that agreed or disagreed. And that's implemented by a decision network, which you see here. The idea is that two different iris codes that are generated conceptually on the left and on the right are compared with each other simply by exclusive OR, vector exclusive OR, to calculate the fraction of bits that agreed. And we just ask whether that fraction is consistent with these being independent bit streams or not independent bit streams. A very simple, almost a trivial mathematical test which performs the pattern recognition here. This is also the reason why searches are so fast, because the decision process is so trivial. We can perform searches on a PC at the rate of about 100,000 irises per second, because all that's involved is taking the exclusive OR of two iris codes, which of course detects disagreement between the corresponding bits, and moreover is a vectorizable operation. So on a 64-bit processor, in a single, virtually in a single machine instruction, you can take two integers, each of whose binary representation is 64 bits long, and generate a third integer, also 64 bits long, each of whose bits is the exclusive OR of the two corresponding bits, the integer implementation of Boolean operators. And that means that you can crunch through iris codes at an enormous rate because of the inherent parallelism of the comparison process. What does the distribution look like when we compare different iris codes? This shows the outcome of tests from that British Telecom have conducted in the last 2 years, involving almost a quarter of a million iris code comparisons. This is the actual data. The histogram shows the percentage of bits that disagree when two unrelated iris codes are compared. And as you can see, it's extremely well described by this solid curve, which is Jakob Bernoulli's function for the binomial distribution. More importantly, besides just telling us that we have a well-described distribution, it tells us how many degrees of freedom there are, how many independent dimensions of variation there are when in different iris codes. And as you can see, it's almost impossible, when you compare two different irises, it's almost impossible to end up with a Hamming distance down in this region, which means 30% of the bits by chance disagreed and 70% agreed. You're almost certain to get much closer to 50-50 as you would with coin tossing. So this is why simply asking how likely is it that you would get an agreement greater than a certain amount and comparing that to the binomial distribution tells us how to make decisions about person's identity on the basis of iris patterns. I mentioned the lack of genetic penetrance into iris codes. I'd like to show you some data which compares 648 genetically identical irises. Now, it's a bit hard to find 648 identical twins, but it's, of course, quite easy to find 648 genetically identical eyes because everybody has two of them. And so this is equivalent to doing the comparison on identical twins, but of course it's just based on the right and left eye comparisons of individuals. And as you can see, although it's just less data than in the previous distribution, clearly it's the same kind of superimposed them. It's essentially well described by the same curve, and so we have what this means is that iris patterns are not genotypic features, but phenotypic features. They are structures that arise from development and are not genetically encoded. Of course, we have to do comparisons over many different orientations because people's heads are tilted and the eye itself rotates in the socket. Doing the comparison at many orientations and keeping the best match gives us this distribution, which is skewed to the left because we've sampled, you've sampled several times from a distribution to keep an extreme value. There's a theory of extreme values of distributions, and we understand the curve that it should generate, and that is this curve. It's something you can easily compute from the cumulatives and densities of binomials. And again, it's the same set of data, the same 250,000 British Telecom comparisons, but sampling for the best match after rotations, and you get, once again, a very good fit. Now, this theoretical curve is important because it tells us, even though there's no data down in here, we never find different people whose irises agree in 70% of the bits, so they get a Hamming distance, down in this region. But it tells us what is the theoretical likelihood of getting any given degree of match from the functional form, because we understand these distributions from Bernoulli trials. And these numbers are really almost embarrassingly, they're astronomical. Even getting 25% of the bits to agree in two different iris codes has a probability of 1 in 10 to the 16th. That's a million times greater than the human population of the Earth. And then, of course, as you get matches down in this region, the chances of a match occurring by chance to that degree of agreement is really vanishingly small. Finally, that tells us what is the decision environment for iris recognition. The pair of the two distributions you get for when you take different images of the same iris over time, that's this distribution, versus images of different irises, and clearly these two distributions are well separated. This is a problem that we can solve just by making a decision criterion in here. We get reliable identification with a theoretical crossover error rate of about 1 in a million when the criterion is there where the C is indicated. You can, of course, be more conservative or more liberal in the decision criterion by moving to the right or to the left. That generates a table of error probabilities, more conservative, sort of government military applications, or more liberal for banking where you don't want to alienate the customer. And the integrals, the cumulatives under those two distributions as a function of the decision criterion is shown in this table. And as I mentioned, the crossover error rate is there. I think my time is up, so let me conclude with a list of possible applications of iris recognition and a list of the current licensees of these algorithms. there are, of course, all kinds of applications in which we need to confirm our identity with either with secrets, like passwords and PIN numbers, or with special possessions, like keys and cards and so forth, neither of which really confirms anything other than that the secret or the possession was present at the transaction. It doesn't establish that the rightful holder or owner of the secret or the possession was there. So that's the point of a biometric identification. And there are lots of applications that are easy to enumerate. The current licensees of these algorithms are listed here in various countries. You've probably seen the trials in cash machines at the Nationwide Building Society. And finally, in view of the news just out last night that a new solar system has been discovered, I couldn't resist showing you one of the consequences of iris recognition as news began to leak around the galaxy. You know, the euro is becoming legal tender in many more places, all over the galaxy, and ironically, this particular cartoon appeared in a magazine called Private Eye.
Thank you, John. In spite of the reference back to the sort of maths that was done on EDSAC, who'd have thought we'd be messing around with eyes in the computer laboratory 50 years later? Our last speaker also came to us from abroad, Ian Leslie, this time from Canada. And I have to say he displayed a little more imagination than the last speaker because he didn't come from Cambridge to Cambridge, but from Toronto to Cambridge, so different names.
Toronto.
All right, Toronto. He started as a PhD student here, and he's remained ever since, till he became most recently our newest professor. Now, he's a little less time. He's in fact only half the time of the previous speakers. This actually is for his own protection, because he's doing something rather risky. He's going to be doing some forecasting of the future, and we thought we'd better not give him too much time to say too many things he might regret later.
Thank you, Karen. I took my mission a little bit differently. It was to only have 15 minutes in which I had to avoid saying anything concrete about the future. But what I think I'll do is try to say a few things about the future, which may not be predicting it, and try to understand what the role of the laboratory is over the next, well, hopefully 50 years, and what we're doing with the heritage that we have from the past 50 years. I think it's fair to say that we find ourselves as an academic department in a subject area which has high commercial interest in the outside world, and that we can't ignore the fact that that puts certain forces at work. Rather than predicting the future, I'm going to try to hand you a kit for predicting the future. I'm going to use perhaps an analogy that John Taylor has put forward, talking about technological discontinuities, or perhaps what I would prefer to call as strains at work, and how that gives rise to opportunities. I will give you a few examples which relate to things going on in the department currently, and then rely on you to go away and apply that to predict the future. This will avoid me having made any predictions. I would like also, just for a moment, at the end perhaps, to actually say there's a hard part in all this, which is looking at research which doesn't fall into the category of strains, opportunities that are obvious, even if they're 4 or 5 year opportunities, and the importance of maintaining the ability to carry on research in that area. So in other words, I may be one of the people in the department that's seduced by strains and opportunities, but we all shouldn't be. Okay. In order to avoid talking about the future, I'll say a few more things about the role of the laboratory. Frank has already mentioned that we're under pressure, again, from outside forces to engage in training people rather than educating them. Also, we sometimes come under pressure to do development work rather than research work, and of course, what's research for one person is development for another. And I'll say a few things about that. And then again, returning to concept, I think, a word that I sort of like recently is about responsibility. Responsibility to the subject in this case. We often hear that we have a very high value industry in the UK and the world economy, which is desperate for more trained IT workers. And we see pressure from funding bodies to direct us to respond to that need. Unfortunately, industry changes so quickly that the notion of training people to fit in today's mold of what IT is or what the skills that are required are is really not our job. We need to produce people who can adapt to the future so that, as Frank says, by the time they've left here, they're not using things that were actually out of date, perhaps on the day they were taught them. More importantly, and I think we have a pretty good track record at this, we need to be able to produce people who shape the future. And I think we can look around a lot of people that are here today who've come through this institution and have done precisely that. We're also, perhaps more explicitly, under pressure to provide more industrially relevant research. There's even a form on front of your EDSAC grant applications that says relevance to beneficiaries. In an unguarded moment, Robert May, the government's chief scientist, said, well, the correct thing to put in there is yes. Industry becomes concerned with shorter and shorter timescales. If things are obvious enough that some benefit is in place, there is some sort of activation energy or some sort of cost in getting from here to there. If the activation energy is small enough and the reward is high enough, industry will do that. So we should be particularly concerned where it's difficult to find that activation energy. It may be longer term, maybe just less obvious. But we also have to help industry find that activation energy, so there's a role, but we should do what we're good at, not try to do the things that industry should do. At the same time, again, it's something I think we're fairly successful at, is to produce people who can help industry. Finally, before I do actually talk about the future, there's a responsibility to the subject that the department has, and that is to maintain and increase a body of knowledge free from commercial hype. Notice I used the word commercial hype. It may not be free from hype, but at least it's free from commercial hype. And certainly in the area in which I work, sort of systems engineering, if you like, it's often said there are no new ideas. It's just that you take the correct one out of the file from 20 years ago and discover that it has new application. Well, you may think that that is a bad thing. I think of that as a good thing. That shows that there is a body of knowledge which is important to look after because it is going to be useful again. Also, we have to realize there are ideas that may take a very long time to have application. May not have an application that you can identify, but increases your understanding of the subject in general. Or, quotes, just be academic. All that means to me is this is probably a very good idea, we just don't know what to do with it yet. But if we put it into that very large body of knowledge, one day we'll come back and be very happy we did that. Okay, now I'm going to come very dangerously close to talking about the future. We've all been hearing about the rapid changes that occur in the industry, in the technology, and how that can give rise to opportunities. Some technologies change predictably. We've heard about Moore's law. It's almost a self-fulfilling prediction. You look and see how fast your chip is supposed to go this year, and you build it so it goes that fast. But the rates of change of different technologies are often different. We've seen processor speeds growing faster and faster, and memory speeds not for quite a long time. So if you like, you have this strain between those characteristics which says the architectures you may have used before are no longer the right thing to do. Another thing that's very interesting, especially perhaps in the past 10 years, is thresholds with respect to human perception have been crossed. And if you really want to carry this strain analogy too far, you can say, of course, there's a strain in that humans aren't evolving as fast as the power of computers is increasing. So old solutions are no longer appropriate, and it becomes possible to do something dramatically different. And I think the latter of these is actually what John Taylor would refer to as a discontinuity. So let's take a very, very quick few examples. Self-time logic, speed at which that gates can produce outputs are getting faster. Distances across the die size we use in silicon is about the same, and unfortunately, another discontinuity, the speed of light isn't going up. So the propagation delays stay the same, and suddenly, clock distribution becomes a critical limitation. So it gives rise to new techniques for managing asynchronous design, the things that we tell our undergraduates are used to when they came in the door. Under no circumstance should you do asynchronous design, because you will come unstuck if you do. And now we're saying, well, actually, because of this real discontinuity, we have to go back and re-examine that. Operating systems, my area, or one of my areas. Crossing the threshold of human perception. Things are fast enough to process, store, acquire, communicate continuous media across a network. So suddenly timeliness becomes part of correct behavior. So, I'm not going to make a prediction. This is the recent past rather than the future. Here's a picture of how operating systems, at a very fluffy level, behave. We have above the black line applications sharing a processor on which there's an operating system. Operating system below the line consists of a number of modules. Each of these boxes, whether they be application or modules in the operating system, have been handed resource in order to carry on their tasks, and the applications call on the lower levels inside the operating system to do things on their behalf. And this is a way many operating systems are built. If you're not an operating system person, you can just think of these things below the line as places to interfere with other people, because as an application you are trying to use resource in competition with other applications below the line, which are in turn perhaps using other lumps of resource further down at the bottom and providing more interference, so the performance that you get at the top becomes slightly unpredictable. You don't know what other applications are going to do, and there's no accounting in the bottom going on saying who's responsible for what. If timeliness is important, we need to guarantee applications that they can paint the next frame up on the 33 millisecond time scale that they have to do that, or get the audio sample out in time scale they have to do that. So we can restructure operating systems. This is something you may see in a demonstration if you wander around, where we actually get rid of this notion that operating systems providing services and operating systems providing protection are one and the same thing. We separate these things out and find that there's very little that actually has to be protected, and applications can run their bit of the operating system themselves. And this is the notion of a vertically structured operating system. And then parts of the operating system also are running in competition with applications in order to provide the services that are required. Okay, the last example I'll use is again a communication example. The trouble is there are too many discontinuities. There are too many things happening. All of a sudden we have networks which were built for a particular reason, or are about to be built for a particular reason, but we don't really know what the applications are going to do. So we can't optimize today. We don't have no model of what the traffic is going to be like, and we need to provide systems which can be changed rapidly. So I've just gone through very quickly a change from a horizontal model to a vertical. So the conservation of concept says we have to move some vertical system, which is the way telecommunication networks are built today, where you go out and buy a solution which consists of all the hardware and all the software, and move to a system in which you divide up the software which runs on the network for the provision of hardware. You create interfaces that allow the programming of the network. So in other words, you're turning the network into something analogous to a computer on which people can run different programs in order to provide this rapid adaptation to new problems. We've heard a bit about computer and human interaction, this strain that people aren't evolving as fast as computers. New forms of interaction, I think we can be very confident that this is something that's going to happen in the near future, and already to some extent is. Augmented reality, people like Peter Robinson have worked on. Immersive content, where the human interaction really involves the ability to interact at a fairly high level with computers, where you actually may have characters which are being provided for by the computers. Finally, coming back to strains, perhaps the biggest strain for me is that when I look out and see the success of the web, I worry about the fact the world economy may come to rely on the internet fairly soon. And I certainly am slightly fearful that we are relying on a lot of things that we don't understand. Again, because applications are changing so quickly, we don't really understand what that infrastructure is going to be hit with. That's slightly worrying. So we clearly need to understand more about the systems we build. Oops. And we need, perhaps more importantly, to understand how to build systems which are understandable. Long-term research. Some of these things I've talked about are in some sense obvious. So what I expect you to do, or want you to do, is go away and think about discontinuities. But there are other aspects of the subject which are not like that. They are just long, hard slogs of making progress against some boundary which is perhaps hard to quantify. And universities are clearly in the best position to carry on this research. It's what we're traditionally good at. And just because there are opportunities out there which people like me can look at and decide that, yes, there is something that in the next 5 years should happen and I should be involved in that, we can take advantage of our perceived relevance by those who fund us in order to carry on research in those areas. But at the same time, we can't neglect, if you like, the purely inquisitive, the long-term research for which we just have, or generally are only able to provide warm feelings about, as opposed to applications for today. I think the only last thing I would say is to go back to the slide before, is that we have a tradition in this department of building systems, and we must not lose that tradition of building systems. But it seems to me that this strain between understanding and reliance means that we have to now focus more about building systems that we understand and leave industry to build systems that capture the next cycle of startup companies or whatever. So let me leave you with that. There is a very bright future ahead across a range of areas. The range of subjects that the department is engaged in is increasing. We're expanding. We need to expand in order to maintain our breadth across the subject. But let us try to use our heritage of building systems and to use our abilities now to analyze those systems in order to move on to perhaps a more solid foundation. Thank you.